Oh, so this is chapter 11. We're studying chemical kinetics, and we're starting with the area of empirical kinetics, where based on data, we can talk about reaction rate and get some other properties about chemical reactions. So last class, we saw that certainly if you were to gather data about the concentration of a reactant or product over time, and your data starts to decrease like this, you know that's a reactant. And if your data is increasing, that's a product. So that's a concentration versus time set of data. But if you were to just dwell on the reactant and vary the initial concentration of the reactant and see the effect on rate, you know that rate is proportional to the concentration of reactant. If you start out with a lot more, you'll end up with a faster rate. But that proportionality, it could be direct, it could be to the first power, it could be a line, but it also could be curved because that's a proportionality. So figuring out that exponent there to the first, the second, the third, whatever it could be, has to be based on the data and is unique for every reaction. So this proportionality becomes an equation, R equals some kind of proportionality constant, we'll call it the rate constant, times the concentration of reactant raised to a power. So this thing is called a rate law for a reaction or rate expression. It summarizes the relationship between concentration of reactant and rate, how the reactant impacts the rate. So for empirical kinetics, the goal really is to determine the rate law for a reaction. That phrase, determine the rate law, means you just have to get the value for the order, that exponent, and the value and units for that rate constant based on data. If you can figure out what to put here and what to put here, then you have determined the rate law for a chemical reaction. So we were looking at this data from last class, and this is the decomposition of acetaldehyde. And we said, oh, there's two trials, and we can sort of eye it up a little bit. If you take between trial 1 and 2, if you were to realize, oh, that's just doubling the concentration of the reactant, what's the impact on the rate? It quadruples. Okay, so we predict a exponent of 2. And so if we want to find the rate law, determine the rate law for this reaction, we're trying to find out what that exponent is. That's called the order of the reaction. We guess here, oh, it's second order. We can see it from the data. And then once we find that value, we can find this value. But what if the data isn't so clear cut? Like, what if you can't eye it up? Well, then we need a technique to determine it mathematically. Oops, sorry. So what's our technique to determine it mathematically? Well, we should take our data and arrange them in the form of the rate law. So here the rate for trial 1, 0.085, and then set that equal to the K, which is your unknown, and the concentration of the reactant in that trial, and set those equal and raise that to a power. And then I got trial 2 there as well. So I have 2 equations here and 2 unknowns. If I want to mathematically solve for these, I want to find the order first. Find this first. I'll say find first. Okay, let's see. I got to combine the equations. Well, one way to do it is to divide both equations. If I divide these 2 equations, that has the wonderful advantage here of, well, K divided by K is just 1. So now I'm going to end up with 1 equation with 1 unknown. Oh, that's fantastic. So 0.085 divided by 0.34, well, that is just 0.25. And I'll set that equal. Now I have 0.1 raised to a power divided by 0.2 raised to a power. Well, that's the same thing as 0.1 divided by 0.2 raised to that power. Both of these are raised to the same exponent. So when I do that, 0.1 divided by 0.2, that's 0.5 raised to this unknown exponent has to equal 0.25. Now we can solve for that m. I mean, we can eye it up again. This is like 1/4, this is 1/2. How do you turn 1/2 into 1/4? Well, you got to square it. If you square 1/2, you'll get 1/4. Still, that's just kind of, because the numbers are nice and round, we can round it, we can eye it up. But otherwise, how mathematically do you solve for an exponent? How do you solve for an exponent? Well, hopefully you have this paper. Okay, you have this handout here, which is titled Fun with Logs and Logs. That's LN. LOG, right? Logarithms, that's the way we can solve for an exponent. We've done a lot of these log rules. We've got more to come, but let's look at this one. If you were to take the log of something raised to a power, that's the same thing as taking that power and multiplying by the log of the something. Take that A and just like bring it down in front. Now it's no longer an exponent, so we could just do regular algebra. So let's try that. Let's take the log of the side of the equation. If you take the log of 0.5 raised to a power, that's the same thing as bringing that power down. M times the log of 0.5. That's nice. And now, if you take the log of the right side of the equation, you have to take the log of the left side of the equation to keep them equal. So now M is equal to, I'm going to divide both sides of the equation by this log of 0.5. So I got log of 0.25 divided by the log of 0.5. Yeah, so we just put it in the calculator. I mean, so if you have a nice simple calculator like mine, if you put 0.5 in there and you take the log of it, like you have to kind of put the number in and then take the log. But fancier calculators, you have to hit log first. So you decide what you're going to do. So if I take log of 0.25 divided by log of 0.5, then that gives me an M equal to 2, as we knew all along. So that tells me the order in this rate law is 2. It's a second order reaction. Now we still got to get this K thing. So how can we get K? Well, we could use either equation or both and average them. So I'll just take the first one. If I put my 0.085 mole per liter second is equal to K times 0.1. Now I know what M is. It's a 2 squared. And I want to solve for K. I got to bring my 0.1 squared over to the other side. Now that 0.1 has units of mole per liter. So that's a mole per liter squared I'm bringing over. So one of those mole per liters will cancel. And so that means my K value, when you solve for it, is 8.5. And my units are liters per mole per second. All right, so there's the K value. And if you do it with trial 2, it comes out to be pretty much the same. It's a constant for the reaction. So within experimental error, that's our K value. So now let's sum up. Let's write out the rate law for this reaction, decomposition of acetaldehyde. So rate is equal to 8.5 liters per mole per second times the concentration of our reactant raised to the second power. There we go. We determined the rate law. We found a value for order, and we found the order first, and then we found the K value. Okay. So what good is this? So when we're determining a rate law and getting values for order and rate constant, that allows us to use that rate law to do other things, to make predictions, especially making a prediction where you want to start with a different concentration of reactant and you don't have the data for it, because a law is just a summary, a pattern. So we have the pattern, so now we can make some predictions. Later, we'll talk about how the rate law has other implications that will guide us to the proposal of a mechanism. But right now, let's make a prediction. Let's take this and say, okay, for our data, we started with concentrations of 0.1 and 0.2 molar. What if we wanted to know what the rate is? Let's predict the rate if you start out with a concentration of 0.5 molar. So if the concentration is 0.5 molar, then you just square that, multiply by your 8.5, and then you calculate that the rate predicted is 2.1 mole per liter per second. 2.1. So that allows us to make that prediction. Right? So that's a pretty high concentration compared to the data. So yeah, the rate predicted is higher than those. Now, of course, relying on just 2 data points, that's not great. I mean, you really want to get lots of data points, but just on the basis of these 2 data points, this is our claim. We can make that prediction. Okay. So let's try another one. Here's another reaction. And so for this reaction, we're not going to name the chemicals. We'll just represent the reactant with A, and it's splitting apart into 2 products, B and C. So it's really about the A. A influences rate. So here's again just 2 trials, okay? Concentration of A and that we start with, and then the rate measured, concentration and rate. So I wrote out the 2 trials, and what are we doing? We're trying to determine the rate law. So we want to find values for M and K. So what do? We'll try to eye it up a little bit. Looks like you cut that in half, and all right. Well, let's go ahead and calculate. Let's divide the 2 equations. That cancels the K's, and so we have 0.085 divided by 0.019. So the left side is a 4.5, and then we have 0.1 divided by 0.05 raised to the m power, which is 2. 2 raised to the m power. Okay, so then I want to solve for m by taking the log of 4.5 and dividing it by the log of 2. So I put those in the calculator. Got 4.5 log divided by 2 log, and that gives me, it's not clean. It's like a 2.2. So it's not a perfect integer. So if we were looking for an integer, we'd choose 2. We'd choose second order. So it means the data measurement, it's a little bit of technique error in there, or maybe there's some systematic error. It'd be nice to have more trials, but that's more realistic. So the 0.2 is kind of a little indication of some error. But we'd say, hey, if we're looking for an integer, it would be second order. And then if we wanted to find K values, we could put in the second order and solve for K. All right, so next video, we'll do a bit more.